So that homework's due Friday. There's two of them. There's that statics project one where you write down some information about your major, what your major is, try and meet some people in your major. And then I had you write down some different subdivisions in your major and companies you could work for on the front. And then on the back, I had you write down projects you could work on and sources of load in those projects. That's due Friday. A lot of you turned it in already in class here. And the idea was just to get you to meet a few people in your major. Now, those of you online, I set up a forum there. If you want to try and meet some people online, that would be fine. If you are online, I realize that might be hard to, meet people that you might like to in your major. So just do the best you can on that. Don't worry about it if you can't find other people, if you're online especially. And then just fill that in as best you can. Yes? No, I just soon, that comes up. There are some people who kind of do a little bit online, a little bit in class. I just as soon have people turn in paper if they're, if they can get it picked up too. That'll probably work better for me. It's just easier to grade paper, but you can always turn the stuff in online too. Okay. So that's just something to fill in, and get in, and then we'll get you credit for that. Are there any questions there? All right. Okay, then we also had a problem with a light fixture. That's 112. So we have this light fixture. We're going to hang it from a cable. We want to find the force rating in the cable in newtons and pounds and use a safety factor of 2. And then use the proper homework format shown in class and include a sketch. So we just need a simple sketch. And the one thing I want to emphasize on this is the format. You want to come up with something like that where you want your name, the date, problem number, and page numbers across the top. You want to paraphrase the problem statement. You don't need to write it all out, but you do need to paraphrase it. And keep in mind you have a safety factor of 2 on that one. All right, so you want to create a sketch like that. Are there any questions regarding this? I think what I would point out here is kind of an important thing. Often when, we're in the metric system there, we often write things in, or call things out with a mass. A person in the metric system, I think their scales would actually read in a mass. And so we do need to convert that into force. See, that is a mass. You need to convert to force is what you need to do to rate that cable. And that would be in newtons. And pounds, okay? And the way you're going to convert that is we have that Newton equation, F equals ma. Well, when you're doing weights, that converts to the weight is equal to the mass times whatever gravity is. And on your formula sheet on the right-hand side, you have gravity both in the English and metric system. So I think that's the basic equation to use there. I am asking you to use a safety factor of 2. So what that means is you'll double up your, whatever weights you get. You're going to want to design that cable for twice whatever the weights are that you get. And that's what you'd want to do. Are there any questions on that? The calculations actually are pretty straightforward on this. Just remember to include that factor of 2, and you're going to need to find out the value of G and then maybe do a conversion there from English to metric system, I think. The metric system we call it the metric system in this country. It's actually called the international system, but of course this was all developed when French was the language that was used around the world, so they have a different word order. So instead of international system, they have the French words for system international, and the SI system is the other word for it. So we're doing all right with that? We got any questions on that? Okay. Yeah, sure.
So you convert to force in newtons and pounds.
Mm-hmm.
So you just want us to convert from kilograms to pounds?
You could. I mean, there's different ways to do the conversions. I guess, let me kind of broaden out your question a little bit. The question is kind of how to convert and, a little bit how to approach it. you could, any of these problems, you can approach them in any way as long as it's logical and it makes sense and it's laid out in a way where I can follow it. You know, I'm not a stickler on exactly how you do it. So you just need to get, you're going to have a mass in kilograms. I'd probably go into newtons first, because that's all in the metric system, and that's pretty easily done using this equation. And then could probably convert the newtons into pounds is probably what I do. Though you could, being as it's on Earth, you could convert the kilograms right into pounds too if you wished. You know, and I guess the thing is, I don't expect you to do it a certain specific way so much as I want it to be logical, and I want to be able to follow, you know, however you're approaching it. I don't know if that answers your question or no. Okay. So, right. So we good on that? Anybody? All right. Yeah.
So, what are all of those problems two?
No, just the
those
two.
Oh.
Yeah, that's another thing. Let's see, the packet, when you get that, you're going to have a lot of problems in the front. Now, the way the packet is laid out, and everybody should have a copy of that and should be bringing it to class. The first basically 30 some pages are homework problems, and they're listed. I don't assign all the homework problems. That's the group I can pick things out of. Is that kind of your question?
Yeah.
Yeah, okay, I'm just picking ones out. I don't assign them all. The other thing is, you'll notice that they're numbered 1 through about, I think it's about 34. I also put in pages in there 1A, 1B sometimes, or 2A and 2B, where I do the problem write-up for you. Okay? So if you have the packet, flip through to page 2 maybe, and then look at the page right behind page 2. It's that piece of graph paper, right? Okay, look at, there's like a 1A, right? And see what I'm saying there, that's for a problem, and the problem number is on there. Is that correct? Okay, that's 122. So what's happening there is I want you to learn how to write up problems correctly, and when you do them on your own, to set them up in the format that I was just talking about, this format. But I also recognize that you're under, let's say, a lot of time pressure when you're a second-year student. So what I do, I write up about half of them for you. They're in there, and they're like pages 1A, 1B, 2A, 2B, etc. They're written up for you and ready to go. You don't need to do those on your own paper. You can just use the paper that I give you when I write them up and just do them right on there. My intent there is just to save time, you know, for you. Now, if I don't do that, you need to write them up yourself in that format. I do want you to learn to create your own independent, good-looking piece of work, you know, that is done properly and laid out properly. But I do set up some of them for you just to save you time. So when I do that, go ahead and use the paper that's in the packet. Okay. Now the second half of the packet actually starts on page 110, which might seem a little odd, and then it's numbered by tens. It goes 110, 120, 130, 140. The reason for that is I'm constantly changing the notes. And if I want to add a page, then I don't have to put in page 111 and a half or something. I can just put in, you know, if I've done 110, 120, I can put in a page 115 if I want to add something down the line. That's why those are numbered by 10. So they're numbered rather oddly, because I have put some pages in there, but they are numbered sequentially. So, you know, I'm sure that 140, wherever it is after 130. It might be a few pages after 130 if I've inserted 134 and 136 or something, okay? So that's how this is put together. It's, I don't know, it's not quite to the level of a book I would publish or anything. It's kind of a loose set of notes, and I change it all the time, so that's why it's done that way, okay? So the front of the packet has the homework, which has those extra sheets in there where I do problem write-ups for you. The back of the packet has the notes, and it's numbered rather oddly by tens and sometimes less when I've already inserted new pages in there. All right? Yeah, question there?
Yeah, on the other end of that question, what all is due on Friday?
What's due on Friday is problem 112.
Okay.
And then what I call the statics project, which was that little group work thing we did.
Okay.
And that's listed in Moodle, okay? I have an assignments list in Moodle where I call out the problems that are due, and then I have the due date.
Okay.
And also, for those of the students who are online, I have an upload portal for them too, though you wouldn't need that if you're in class. Just turn them in class. That's all you're going to do on paper. Yeah, sure. And you know, if you've got any questions, ask. I mean, it's just better to get that figured out if there's questions on any of this stuff. So, you okay? All right. All right, so typically at the start of the class, if there's questions on homework, I'll take them. That's normally how that works. And then we just get into some more new stuff. We always keep going through the material. All right, so we good? All right. Okay. Well, let's have a look at some two-dimensional forces. Let's start with that because an awful lot of things in engineering are done in 2 dimensions. So you see that truss bridge out there. That's the old railroad bridge in Salem that goes over the Willamette. If you look at that, even though it's a 3-dimensional object, it can be designed in 2 dimensions, X and Y, if you look at those panels. Okay, so let's have a look at some stuff with vectors. Now this is on page 120 of the notes, I think. Right now, the way this stuff works is we get these mathematician types who are really smart and like playing around with relationships, and they come up with stuff. And then maybe 100 years, it used to be 100 years after they came up with it, some engineer would come along and say, oh yeah, I can use that to model this, So a scientist named Descartes came up with this idea of a vector. His big thing was combining algebra and geometry together and coming up with analytic geometry. And that was really pretty, I think this scientist is pretty smart. He's a pretty smart one. He was one of those people that did philosophy and science and math and all this crazy stuff. And this is one thing that he came up with. So he came up with what's called a Cartesian coordinate system. That comes from Descartes. Okay. So this is a nice little model that we use to model our forces. Okay. Now there used to be a 100-year lag between the mathematicians and the scientists and then the engineers, but now it's probably more like 2 months or something. I don't know. I mean, the pace at which things are changing. I do remember there was a thing with the theory of relativity where Einstein put a little note in there thanking some mathematician who came up with some equations that, some sort of relationships that Einstein could use to model part of his relativity theories and all that. So, this is a kind of a relationship where the mathematicians come up with stuff that the scientists and the engineers use to model things that we see out there in the world. Okay, so Descartes came up with this idea of a vector, I think, or at least the theoretical basis of it, and we use it, okay? So let's kind of have a look here. So a scalar is a positive or negative quantity. It is a quantity only. So I could say that I have a mass of about 80 kilograms, I think. That doesn't point any particular direction, it's just an amount, okay? A vector has a magnitude, which is an amount, but it also has a direction. It points a certain way. Okay, so my weight points down because my weight is the force of the earth pulling on my mass, right? So it points down towards the center of the earth. It also uses what we call the parallelogram method of addition. Now there's a notation for vectors. If you do it freehand, you just put an arrow over the letter to designate a vector. So a F with a vector over it usually means a force. A V with a vector arrow on it means a vector, or a velocity, actually a velocity vector. You also use these little hats, these little things that look like that for unit vectors. Okay, so if you're writing out vectors, to call them out as being vectors, you put an arrow or a little hat on the top, depending on the type of vector. If you're typing a vector, you make it boldface. Now we use vectors a lot because they're a very good way to model a force. That's what we use them for. Okay, so if we can multiply a vector by a scalar. So let's say I've got a 30-pound weight. I can multiply that by 2 and double the weight. What I do is I multiply the 30 times 2 and get 60, and I keep the same direction down. Okay. So twice a 30-pound weight is 60 pounds, and it goes down. All right. All right, now when you add vectors, you can do it 2 ways. See, the fact that they're directional makes the addition a little bit different. It's not arithmetic anymore because the vectors have direction. You can put them tail to tail, as I'm doing there. So I've got vector A and vector B. I can put them tail to tail, so the ends of the vectors are put together. I can then draw in parallel lines to each of the vectors and look where those parallels intersect. And then I can connect the tail-tail intersection to where those 2 projections intersect. That is the resultant vector, as it's called. So R equals A plus B vector style. I can add 2 vectors at a time that way. perhaps a more convenient way to do it is to put vectors head to tail. So the arrow of one vector on the tail of the other. That allows me to add more than one vector at a time. I can add as many vectors together as I want that way. So I prefer the head to tail method when I'm doing it. Okay, and here's my first vector, there's my second. So I start at the beginning, at the tail, and I go to the head, like that. Okay? So the resultant vector is A plus B. I can also subtract vectors by turning the thing I'm subtracting around, pointing it in the opposite direction, and using the head to tail method too, so I can subtract vectors that way. Okay. So that's how I can work with vectors a little bit. And I do want you to have that picture in your mind when we add force vectors together. That's really what you're doing, okay? Now I can also do the reverse of that. I can take a vector and find what I would call its components, which are two things you would add together to get the total vector. I can put the vector in two space, in a flat plane. I can put two axes on there. Now normally I like my axes to be perpendicular, but they don't have to be, so I didn't draw them that way because they don't have to be. Here's my two axes. Then I draw in parallel lines to the axes to the head of the vector, and wherever those intersect the axes, that's where my components go to. There are the two components of that vector, m and n. So I can say that m plus n is equal to r. Okay. Those are just some rules of vectors. Now, vectors are a very good model to represent forces. Forces are added together as vectors. And often we want to add forces together. We want to know what the effect of having multiple forces on an object is. All right. So are we good with that? Okay. All right. Now let's have a look at an example of this. Let's say we're going to apply these three forces to that bracket. So I'm on the next page, which is page 130, is it? Okay, 130. There we go. All right. So I'm going to put those three forces and apply them to the bracket at A, and I want to know what's the net force at the wall, okay? So if I'm going to attach that bracket here to the wall, the hatching means a wall, a solid surface that I could attach to. If I'm going to apply those three forces to the bracket, and I want to know how to connect the bracket to the wall. To do that, I've got to add the three forces together to get the net force. The resultant force is the word I would use for that. So let's find the resultant force and the angle it makes with the horizontal. Okay? Now I'm going to do one of these graphically because it's important that you view it this way. All right? So let's do this graphically. So what I'm going to do, I'm going to put my bracket over here, and I'm going to put vectors in there at the proper angle, and I'm going to use a scale of 1 centimeter is equivalent to 10 newtons. That's how I make a vector, that's how I use a vector to represent a force. I set up a scale so the length of the vector is proportional to the amount of force. So I'm going to use 1 centimeter is 10 newtons. And I'm going to put those vectors together. All right. Looking for a good view of that. Okay, so what I'm doing there, and that's kind of hard to read, but you have it in front of you. I've got 700 newtons. I'm sorry, 10 centimeters is 100 There we go. So I've made that line 10 centimeters long at the proper angle, 53.13 degrees. So that first line that extends out from the bracket at A is 10 centimeters long, and it's and that represents the 100 newtons, and it's at 53.13 degrees. My next line is horizontal, representing the horizontal force. It's 3 centimeters long. That's 0 degree, 180 degrees, I guess I should say. It's a horizontal line. And then the last line is down and to the left at 63.43 degrees, and that is the length that represents the magnitude of the force. Okay, the force is 134.16 newtons, so that's 13.416 centimeters long. So what I'm doing is I'm putting those vectors head to tail at the proper angle, and their length is such that 1 centimeter represents 10 newtons of force. All right, now when I do that, what I can now do to find the resultant is, being as I put these vectors head to tail, is I can start at A and draw a vector that extends out to the end of that third vector that I drew in there. And that's called the resultant. Okay. So now if I want to know what the result is of adding those 3 vectors together, what I can do is measure the resultant with a ruler. Okay. And when I measure that, I'm getting about 15.6, something like that, centimeters. Okay, so the length of that lower resultant vector is about 15.6 centimeters, 15.5, okay? So we'll call that 155 newtons. And then I can get a protractor, and I can measure the angle it makes with the horizontal. So I can put a protractor on there and read the angle, and that's about 15 degrees. So what I can say now is, if I apply those 3 forces, add them together, what I get is a resultant of 155 newtons at 15 degrees down and to the left. So when I connect this bracket to the wall, that's the force I'm going to have to design the connection for. Okay? And that's what I'm doing when I add vectors. Yeah, a question there?
So let's take the safety factor into consideration, and then those 2, you just double that.
Yeah. If I had a safety factor of 2, I'd double the 155, I'd make it 310, and that's what I designed it for. And that's very common. I think a common structural design safety factor is 1.4 or 1.5. Okay. All right. So that's the idea. That's the picture we want to have in our head, okay, of when we start adding forces together. This is what we're doing. So any other questions on that? Yeah.
Would it be a negative 15 degrees?
It would be, you could call it different things, and I think that's a good question. You notice I put an arrow down there at the bottom, pointing down and to the left.
Yeah.
And you could call that different things. I think the things I would tend to call it would be 180 plus 15, 195 degrees. Or I could just, what I prefer, because I'm not so formal in how I approach this. I just like an arrow saying it's going that way and here's the angle. That way it's totally unambiguous. But if I were to give that a real angle like a mathematician, I'd probably call it 195 degrees is probably what I'd call it, yeah. So however you want to do it that's clear is fine. Okay. All right. Other questions? We doing all right? Okay. Now that's the picture I want you to have in your head, but that's not how you're going to do it. We don't sit around all day with graph paper and protractors and rulers. That's not how we work stuff out. We do it analytically, okay? So let's look at that. But I just want to go over that just to show you what you're really doing, okay? Now, a 2D vector, let's look at how we handle this in what I would call in an analytic way. Okay, a 2D vector has components along the x and y axes. So if I have FA, I'm on the next page here, 140, I think, going off at an angle, there are components in the x and y directions, and I can find those easy enough in the x and y directions, all right? Now, the x and y directions can be signified with what's called a unit direction vector that points in the proper direction and has a magnitude of 1. So a unit direction vector in the x, along the x-axis is called I. You notice that little vector hat on that. And a unit direction vector in the y-axis is called J. All right. So what I could do, I have options for how to name this. Now this isn't a big deal. It's more just about notation and how I talk about something. FAX, I could call it that. I could also call it FAX as a magnitude and then I. So that gets it's a magnitude and a direction. I could break it into 2 pieces. Sometimes when you do the notation, you do it that way, especially when you're doing 3D. So I just thought I'd call that out. Okay. But what we're doing there is we're taking FA and we're breaking it into 2 pieces. One in the x direction one in the y direction. So we good with that? Because when we break these vectors up into x and y components, now we can use arithmetic, see? Once things are in the same direction, you can add them together with arithmetic. And what I mean by that is, let's say I've got a vector that has components of 3 and 4. Does anyone know how long that vector would be?
Square root of 9 plus 16.
Yeah, be 5, wouldn't it?
Yeah.
3, 4, 5 triangle.
Yeah.
You can't use arithmetic on this. You can't, because what I got there is 3 plus 4 is 5, right? You with me there? Because they go in different directions. I just can't add them up, okay, with arithmetic. But if, yeah, right, I got to do a hypotenuse. I got to use theorem of Pythagoras. But if they're in the same direction, I can use arithmetic, okay? So if you take these angled vectors and break them up into x and y components, you can then add the like components together, okay, and use the arithmetic then, okay? So if I have those two vectors, a and b, if I first break them up into x components and then y components, I can then use my arithmetic, see? I can go fax plus fbx, that's the I part, the x, that's the resultant vector in the x direction, and then I can do the same thing in the y, fay plus fby, and that'll get me the total y component. So that's what you do when you're doing this analytically. You take the angled vectors and you break them up into x and y components. Okay. All right, so to generalize this, the resultant vector in the x direction is the sum of fx, okay? And the resultant vector in the y direction is the sum of fy. And the resultant vector then is the sum of the two, sum of fx plus sum of fy. Okay. Now, quite often when I do that, I'm going to want to know the magnitude, how big the resultant is, and also what angle it acts at. And I can use the theorem of Pythagoras there to get the magnitude, and I can use an inverse tangent to get the angle. Okay? So I can take the resultant vector as sum of fx squared plus sum of fy squared and take a square root. That's the theorem of Pythagoras. And the angle then of the vector is the arctan, or the tan to the minus 1, whatever you want to call it, of sum of fy over sum of fx. Okay? So that's how we do this normally. We run through this with a calculator. We use theorem of Pythagoras, and we use some trigonometry, and we work things out. That's how you actually do this. I wanted to do the graphical thing just so you had a picture in your mind of what you're actually doing, but the calculations are done with trigonometry and a calculator. Okay. So we got any questions on this? Now, there's one little thing about that arctan we got to be careful of, though, and that is this. Let's say you've got an angle like so. It's 3 by 4. Anybody know what angle that is offhand? 36.87? You all know that one? There's some numbers I couldn't forget if I wanted to, and that's one of them. The other one is there's 43,560 square feet in an acre. I can't forget that. I'll know that forever, whether I want to or not. Okay, now what's going to happen there is you're going to run those numbers, and what's your calculator going to do? Your calculator is going to do this, okay? Because your calculator does what it's told to do. It's going to take y over x, and it's going to do a tangent to the minus 1, and it's going to do a tangent to the minus 1 of 0.75, right? Now, what if you've got this. I'm just pressed for space here, so I'm gonna have to cheat a little bit. I'm gonna come over here. What if that's -4 and -3? What is that angle here gonna be? Gonna be 36.87, kind of going the other way, kind of getting to that question you were asking there a minute ago. What's your calculator gonna do with that? It's gonna go tangent to the -1 of -3 over -4. And what happens with that next step? What's -3 over -4?
175.
Calculator don't know the difference, does it? Same thing, okay? To the calculator. It's not the same thing to us, but it's the same thing to the calculator. So your calculator is going to go, I don't know what to do, and it's going to look to its program, and it's programmed to output answers in quadrants 1 and 4. That's what your calculator will always do. Watch out for that, because sometimes you have to look at it and say, well, my calculator is giving me this answer, but that doesn't look right. It's actually going that way, okay? So we always got to give it the common sense test, all right? And I remember once I've done surveying when I used to work. I work here too, but when I was doing engineering work, and we were setting a bridge piling for somebody, and I had geodetic coordinates for somebody based on state plane and stuff. And I was walking into the meeting with the coordinates, and there just happened to be a map up on the wall that had latitude and longitude on it. And I looked at that, and I'm worked up in Alaska, and the dang bridge piling, they were going to put it in Oregon, and something didn't quite look right. When I looked at that map, the latitude and longitude was in Oregon, and that didn't look right to me. I was a little late for that meeting, but I turned around and went back and talked to the person on the computer. What they'd done, they switched the latitude and longitude input. They'd done something where they switched the coordinates around. So we're going to walk into the meeting and tell the client to put their bridge in Oregon, which they probably wouldn't want to do because the road was in Alaska. That wouldn't have worked so well. So we always like to look at things and say, oh, does that make sense? Okay, so just be sure, remember this one, okay, because this will come up sometimes. Look at the angle, make sure it's going the right way, okay? So let's redo our problem, but let's do it engineering style, okay? Let's not do it with graph paper. Let's lay it out. All right, so here we go, same problem. Let's do this analytically. All right, now notice how I have this set up. Part of this class is for you to learn about statics, but the other part of it is to learn how to calculate stuff the way engineers do, okay? I want to turn myself into a human spreadsheet is what I want to do. I want to get very systematic about how I do things and pay attention to that. I want to write in a reasonable way. I want it to be laid out and organized for a lot of reasons. And one of the big ones is, if you make a numerical mistake and whoever's grading your test or whatever is doing their job properly, they're probably just going to take a point or two off for that because you just hit the wrong button on the calculator. But again, I've done surveying. If I make a mistake on a grade stake and tell a contractor to put a pipe over there when it belongs over here, that's bad, okay? Bad things start to happen. So you want to develop these real clean ways of calculating things now. Start doing it now. Don't wait till you start working, okay? Take my advice on this, okay? And learn ways to organize your work to cut down on the errors. We all make mistakes, and I'll make plenty here, and you'll catch me on them, and that's all good, and let me know. But cut them down, okay? Because like I say, in school, it's a point out off and kind of, oh man, look what I just did. At work, it's a whole nother issue, man, whole nother issue. So get systematic, get good at this, okay? I've got that laid out and ready to go. Look how we're gonna do this, okay? We got the 3 forces in rows. We've got X and Y in columns. That was all done intentionally because I can just lay it out and just work right through it that way, okay? That's what I'm thinking about here. All right, so let's get these forces broken up. I've got 100 newtons up and to the left at 53.13 degrees. Let's get that broken into a vector, okay? So I can do this 2 ways. I like to look at it and do it that way. I see that this vector, the first one, is up and to the left. Now, what does up mean as far as Y goes? Means positive, right? With me? Okay. What does left mean as far as X goes? Negative, okay? That's how I do it. So that's what I'm doing right there. I've got angles there with the horizontal, So I'm doing some trigonometry here, and I remember my triangle stuff. All right. So what's up with trigonometry here is I've got the adjacent side to the angle is what? Cosine. And the opposite side is sine, right? That's how that works. If you're using an angle with the horizontal, which we don't always do, but if that's what we're doing, that means that sine is y and cosine is x, okay? Now, we're going to do lots of right angle trig in here, so refresh that if you're, this is something you need to be comfortable doing, okay? All right, so what I'm doing there, I'm saying, okay, I got a 53.13 degree angle here. So the cosine will get me the x component, but I got to give it the negative because I'm going that way. I've got a negative x component, so I'm putting the negative in there is what I'm doing. And that works out to be negative 60. And then the y component is sine 53.13, and that's 100, so that's going times 100, and so that's going up at 80, so that's a positive 80. So that's how I'm doing that. And I look at the angle, I build a triangle out of that vector. I look at the direction, and up and right are positive, and down and left are negative, okay? That's how I'm doing that. Now I could also, if I wished, just always take the positive angle from the positive x-axis. So if I take 180 and I take away 53.13, I get 126.87. So I could do it that way. If I do it that way, I don't have to worry about sines. I just put the angle in the trig function and the sine will come out. Okay. Now eventually I'm probably going to work in this class all this way because that's how I learned how to do it and that's how I think. But you could do it the way I'm describing below as well. You could do it either way. So I've done the same thing twice, two different ways. You could pick whatever method you are more comfortable with. Are we okay with that? Mm-hmm. So what I've done is I've broken up the 100 newtons into two components, an x and a y, all right? Let me just look here real quick. How did I do that? I went, where is it? Green and red, okay? There we go. So the green part is 60 negative, and the red part is 80 positive. You all right with that? I'm going to do that 3 times for each of the vectors. I'm going to break each of them up into x and y components. And what I'm going to do, I'm going to list them right over top each other because I like to add and subtract in columns. See? I do it better. I make less errors. And again, it might seem like a boring, trivial little thing to do, but if you're setting grade stakes all day and you set 500 of them, you make a mistake on one, it's trouble, okay? So let's good habits. That's what we want. All right. Now the next one, I don't even have to do trig on that. That's horizontal. If a line looks horizontal and it's not dimensioned, you can assume it's horizontal. The one thing about that is it's going to the left. Okay. So that's negative 30, x, 0, y. Okay. Then why don't you work out the last one? Always a good idea to have a calculator here, so why don't you knock out the last one if you got one. And watch your signs and all that. So a bit of trigonometry there. You've got the angle given. You can either find the angle with the positive x-axis, or you can just make a triangle out of that and do the trig, either way. get the two components and just get them in the right spot. And then you just add up the columns is what you do. Watch the signs, of course, when you add up the columns. You got any questions? No. The negative 60 and negative 120 for those? Does that sound about right? You can do them either way. All right. And then once you've got that, you can just add them up. See? Now I kind of got that a little bit confusing because I've got so many of them because I did them different ways. But you just need to add up each of the numbers. A lot of it might be subtraction too. Okay. Like so. And get the net. Am I all right with that? So when I add up those sets of numbers, negative 60 minus 30 minus 60 is negative 150, and 80 minus plus 0 minus 120 is negative 40. So those are my x and y components. And you know, I add a lot better in columns than I do in rows. That's might sound like a funny little trivial thing, but it works better for me, you know. It's more visual that way. I don't know why. It seems to work better. Everybody good with what we're up to here? We got any questions? All right, so that's the resultant. Now what I want to do, I want to know the magnitude and the angle of the resultant so I can do that, all right?
Pretty close to the measured version.
Yeah, close enough, you know. One thing and that's
14.89 degrees
Okay.
instead of 15.
Yeah, right.
Yeah, that's pretty close.
And yeah, if you're building something, you know, do you care about that? You know, that's always a question I kind of ask. And what I'm doing, it might depend on what, you know, what I'm doing. Okay, we good? So we all got that? Because I'm going to switch the slide over. We're good. We're good. All right, so I'm going to find the resultant. Okay, so to find the resultant, I'm just going to take the sum of the square root of the squares and take a square root. So I got negative 150 and negative 40. And that's going to come out pretty close to 155. Yeah, it does, doesn't it? That's what we got when we did it graphically, not bad. And then I'm going to do the angle too with an arctan or inverse tangent, tan to the -1, whatever you want to call it. Okay?
I was thinking about why tangent to the -1 because it's an
Inverse.
undefined domain from 2 pi to 3 pi over 4.
Okay.
If you graph it as a horizontal asymptote,
yeah.
every 2 pi to 3 pi over 4.
Yeah.
And the unit circle is untrue for inverse tan on the left side.
Okay. It's something like, yeah, you get in infinity. I think.
Pythagorean rules. Yeah, it goes to infinity at 2 pi and 3 pi over 4.
Okay. All right, so there's the resultants. And then the angle, 14.9 degrees. We got 15 with a protractor, you know. I very much doubt if I'm building some sort of structure, 14.9 and 15 is going to be too much different as far as how I build it. I don't know. Might depend on what you're doing and how much you want to pay for it, I guess. So everybody just think about this. After you go through that arctan, which way does the 14.9 degrees point? And we'll just do it on your own. Get an arrow, go in the proper direction. Where is that going? 14.9 degrees.
Southwest.
Okay, that might be one way to describe it, yeah. Okay. So, there we go. So down and to the left. Okay. So you could call it 14.9 down and to the left. I guess you call it 14.9 southwest. You could call it 194.9 if you wanted to. But I kind of like the 14.9 down and to the left. And one reason for that is, you know, in this environment, we could talk about 194.9. But the other thing to remember about engineering is, you know, you're going to spend a lot of time calculating stuff and all that. But when you got to remember when you start working, especially, the goal is to build something. It's not to calculate something. And when you build something, you got to talk to the people who build it, right? And my guess is if I'm talking to a contractor with a sledgehammer in his hand, I'm not going to want to tell him to put that line out at 194.9 degrees. I'm probably going to tell that contractor, go that way at this angle. You know, that's how, you know, you're talking to a different group of people, right? And they think visually. That's often how people who build things think. They don't think quite as analytically as engineers might. Now, believe me, they think very well in a practical sense. Most of what I know about engineering, I learned from people with a high school education who've been working in it for 20 years. And those people knew their dirt really, really well. They knew more about dirt than I'll ever know. And I mean that quite seriously. Okay, they're very intelligent people and very capable, but you got to communicate with them in the ways that they think. Okay, that's important to do. So that's why I kind of like this. There's an arrow, there's an angle, there's no doubt. That's what we're talking about there. Okay. All right with that. That's just a basic example there. So graphically, what we just did is we broke that thing up into X and Y components, and we added up the X and the Y components together. That's what we just did. All right. Okay, so that's what we just did. We took each one of those vectors, broke them up into X and Y components, and then added the like directions together. So as it turns out, that negative 60, negative 30, negative 60 are right in a line. That got us to negative 150. And then the 80 up and the 120 down got us to negative 40. Okay. So there you go. That's what we got. So questions on that? That's a little bit of 2D right there. And that came in quite close to what we did graphically, too. So if you're conscientious, you can get pretty good answers graphically, too. Okay, questions? Okay. All right, why don't we just take a break here for 5 minutes or so? Okay. A little bit of a break.